what does it mean to be rational? What's a rational number? An integer is an example of one. How about an irrational number? The joke gives you a hint. I is an imaginary number. Pi. Pi is an irrational number because it's decimal, does not repeat, and it does not end. A rational number, it's either a repeating decimal or the decimal ends. It can be written as a fraction. Okay? You guys should know that off the top of your heads. So just plain. Okay? We are going to work with rational functions. So functions that are written as a fraction. Okay? So you are going to get something that looks like this. We're going to have a polynomial over a polynomial. Okay? And so here I have my function n for my numerator, function d for my denominator. Okay? Polynomial over polynomial where we do not have any common factors. Okay, I have a hint here. We're going to have to simplify our fractions first. If there are any common factors, we need to get rid of them. Okay, now, luckily we have already worked with the domain of these functions, haven't we? Okay, the domain is going to be all real numbers except whatever x values make our denominator 0. Okay. We already worked with that in our chapter 1. Okay, whatever makes the denominator 0 has to be excluded from our domain, but everything else is okay. Okay, and I'm going to make a note here. We're going to look at the domain before we simplify. Okay. Now, characteristics of a rational function. No matter what, we are going to have a vertical asymptote. We've talked about this already. When do we get a vertical asymptote? How do we know where our vertical asymptote is? We talked about this in chapter 1.
X equals 0.
Not when x equals 0, whatever x value makes our denominator 0. Wherever our denominator is 0, that's where we're going to have a vertical asymptote. Okay, what is a vertical asymptote? Okay, here's the explanation. We have a vertical line where as we get closer to that line, we're either going to approach infinity or we're going to approach negative infinity. The closer we get to the asymptote, okay, we're either going to go to infinity or negative infinity, but we are not going to touch it. Right? We're not going to cross the vertical asymptote. Okay. What's another characteristic of a rational function? We have a vertical asymptote. What else could we have? Horizontal asymptote. Okay? But as you recall from Algebra 2, we have some different rules for finding our horizontal asymptote, and we're going to add another one. Okay. So first of all, when we talk about a horizontal asymptote, okay, we have a horizontal line that as we as we look at the end behavior, we're going to approach that line at infinity and negative infinity. Okay, you may recall from Algebra 2, there was a couple times where your graph went through the horizontal asymptote. That is okay. The only thing that matters is that we approach the horizontal asymptote towards infinity. Okay, all it's really describing is the end behavior. If it crosses somewhere in the middle, that is okay. So do not panic if you get your graph to cross the horizontal asymptote, as long as it approaches it at the beginning and end of your graph. Okay. So there are 3 different situations for our horizontal asymptote. You need to know these, and you need to recognize them immediately. Okay? If the degree of the numerator is smaller than the degree of our denominator, where is our horizontal asymptote? You guys knew these a couple weeks ago. The degree of the numerator is smaller than the degree of the denominator. Our horizontal asymptote is at y equals 0. So if you have a bigger denominator, degree-wise, y equals 0 is your horizontal asymptote, no matter what. Okay, you all should remember this one. What if the degrees are the same? What do we look at? If the degree is the same, numerator and denominator, then your line y equals whatever is the ratio of the leading coefficients. Now, what is going to happen when the degree of the numerator is bigger? If the degree of the numerator is bigger, there's not going to be a horizontal asymptote. Okay. We will talk about this case in a little bit, okay? Because we have a special case where we get what's called a slant asymptote, and we're going to actually graph those. In Algebra 2, you did not graph them. Here in pre-calculus, we are going to graph them, and they're really cool. Okay, but first I want to do an example of each of these first 2. Okay, so I'm going to give you some guidelines, okay, of how to graph these. All right. The first thing you have to do is simplify. Okay? Something special happens when you cancel out factors. Okay? So the first thing you have to do, you need to factor your numerator and denominator and see if anything can cancel. Okay? The book is going to ask you for x and y intercepts. Okay? How do we find those? Y-intercepts, you plug 0 in for x. X-intercepts, you plug 0 in for y. Okay. you're going to want to put in your asymptotes, okay? I would probably draw those in. Your asymptotes, I would probably draw those in first, okay? Before you do 2 and 3, now that I think about it. And then my requirement is that you're going to need at least 2 points per branch, okay? So we're going to strategically pick values on each side of our vertical asymptote, or asymptotes. We could have more than one, all right? But each piece of our function, how many pieces we have, you need at least 2 points so you can get that shape. We know that our curve is going to approach our asymptotes, so we at least know that behavior, but we just need to get an idea where those little swooshes are going to be, okay? We'll use technical terms. Okay, so biggest thing, we need at least 2 points per branch, okay? You need your asymptotes in there, all right? And make sure when you connect your points, everything's nice and smooth. Okay, just like our polynomials, everything is smooth. We have no corners. Okay. Okay, so we're going to do a couple graphs. I will always ask for domain and range. The domain is always going to be simple. The range, we're going to sometimes need our graph before we look at the range. Okay, if there's more than one vertical asymptote, we're going to have to look at the graph before we give the range. If there's only one vertical asymptote, the range we can do without the graph. Okay, so first graph is this one right here. 2x squared over x squared minus 1. Okay, so the first thing I told you needed to do was factor in case we could simplify. So, okay, upstairs, obviously, nothing can factor, or we can't really factor. Downstairs, we have x plus 1 times x minus 1. Does anything cancel? No. Okay. So let's identify, where do we have a vertical asymptote? Where's our denominator 0? 1 and negative 1. Do not write 1 and negative 1. We have the line x equals 1 and the line x equals negative 1. Those are our vertical asymptotes because that makes our denominator 0. Okay? The degrees of the numerator and denominator, how do they compare? They are the same, so our horizontal asymptote is y equals what? 2.
So is that like how many x squareds compared to the ones on the bottom?
Like degree in the numerator is 2, because that's the highest exponent for x. Degree in the denominator is 2, that's the highest exponent for x. Okay? Now, we can identify our domain before we graph. We identify our domain by looking at what? Okay? Everything is safe except where our denominator is 0. So our domain is everything except negative 1 and 1. Okay? That was a chapter 1 concept. Sorry. All right, so now I want to graph this bad boy. I would like you to create a table of values, okay? Or you can label them on here, but it's less messy. First thing, let's go ahead and plot our asymptotes. So we have an asymptote at x equals 1. What I'm going to do, I am going to, just so you can see it better, I'm going to count by halves, okay? So here's my x equals 1, and my x equals -1. Okay. And then here's my y equals 2. Please label your asymptotes when you graph them. Okay? Now, we need 2 points per branch, is what I call it. So let's go to this very left side. I have an asymptote at x equals -1. So let's pick a value to plug in. How about -2? When we plug -2 into our function, what do we get? We get 2 times 4 over 4 minus 1, right? 8/3. Okay? And then I need another point. Let's plug in -3. What do we get when we plug in -3? 18 over what? 18 over 8? So 9 over 4. Okay? So we have -2 8/3 and -3 9/4. And I know that this has to approach our asymptotes. Okay? Now, to make our life easier, I'm going to go to the very right side. Let's plug in, since I have an asymptote at 1, let's plug in 2, and let's plug in 3. What happens when we plug in 2? 8/3. And when we plug in 3? Okay, the only reason it works like that is because my only x terms are squared, right? Okay, so we have symmetry going on here. That's kind of nice. Okay, now we have to figure out what's going on in the middle of these two asymptotes. I will tell you right now, if you have 2 vertical asymptotes, either you're going to have a U, or you're going to have something that snakes all the way through. Okay, you may recall that from Algebra 2. So let's see what happens. Easiest thing to plug in first is 0. What do we get when we plug in 0? 0. Okay, now I need to figure out, okay, 1 point's not going to do us any good. You need 3 points if you in between 2 vertical asymptotes. So what happens when you plug in 1/2? What happens when you plug in 1/2? Anybody? You have 1/2 over -3/4, right? Which is -2/3. And what happens when we plug in -1/2? Same thing, right? So here's our graph. We have the U instead of the snake. Okay? All right, you've seen a graph like this before, yes? Okay? let's talk about its range. Okay? This example is not as simple as everything but the horizontal asymptote. Why? We have a gap here, don't we? Okay? So let's talk about our range. Range means y values. So from top to bottom, we have values down here, right? Where do they stop? They stop at 0. Is there a point at 0? Yes. So we have values from negative infinity until 0. And then where do our values pick up? We have a gap, and then above 2, we have more values, correct? But there's a horizontal asymptote at 2, so it's only above 2. Questions? Okay, let's recap. We simplified, well, we couldn't simplify. We identified our asymptotes, we plotted them. We just picked points to the left and right of our vertical asymptotes, and in this case, in between, to get our shape. Okay, and then we look at the domain range. All right, I would make a table. Okay, otherwise, if you label each point, it's going to get pretty messy. But I need at least 2 points per branch, so you know the shape. Okay. Next one. Okay. X squared plus x minus 2 over x squared minus x minus 6. Okay. We need to simplify. So first of all, let's factor. What is the numerator factor to? X plus 2, x minus 1. And the denominator? I don't agree with that. X plus 2, x minus 3, right? Hey, what happens? The x plus 2's cancel out. Does anybody know what that means about our graph? Do you remember? Okay. If you get factors to cancel, that means you have a hole in your graph. Okay. We're going to have a hole at x equals negative 2 since that is the factor that canceled. We are going to graph this simplified version, but we are going to have a hole at x is negative 2 because that makes our original function, the denominator, to be 0. Okay? So in this case, we only have a vertical asymptote at x equals 3. Okay? And where's our horizontal asymptote? Y equals 1.
Where did you get the
Horizontal asymptote, our degrees are the same. So we look at the coefficients, 1 over 1. All right? So now, when we write our domain, we have to exclude our horizontal asymptote and our hole. So we have everything except negative 2 and 3. We will talk about our range in a second. Okay. All right, so we have an asymptote. Our vertical asymptote is at 3. And our horizontal asymptote is at 1. So x equals 3, y equals 1. When you only have one on each, it makes it a lot nicer to graph, right? Okay, so if my horizontal or my vertical asymptote's at 3, let's pick a couple points to the right. Let's say 4 and 5. Okay, pick nice integer values that are nice to plug in, all right? So when we plug in 4, we're going to plug it into the simplified version. When we plug in 4 to our simplified, what do we get? 3. And when we plug in 5? 2. So you have 4, 3, and 5. Oh, it's not 3 at all. Okay. What about to the left side? Let's pick 2 and 1. What do you get when you plug in 2? And what do you get when you plug in 1? Now, we also have a hole where at x is -2. You have to graph that hole. So where is our hole? When you plug in -2, what do we get? Positive 3/5. Okay, so I am going to graph, here's our 2, -1, our 1, 0, and then at -2, 3/5, we have a hole. Okay, we have a hole because x equals -2 still makes our denominator 0, but that factor canceled. Okay, so now let's talk about our range. What values do we not have for our range? What do we have to exclude? We have to exclude 1. Anything else? We have to also exclude 3/5 because there is a hole there. So our range is everything except 3/5 and 1 because that is where we have a hole and a horizontal asymptote. When you get factors to cancel, you will have a hole. Questions on this one? You will probably see one like this again. All right, so let's talk about our third case. If our degree in the numerator is higher, we do not have a horizontal asymptote. If it is exactly 1 degree higher, we're going to get what's called a slant asymptote. Okay, or oblique. I'm going to call it a slant. Okay? If our degree in the numerator is higher, that means we have an improper fraction, correct? We talked about that, I think, in chapter 1, maybe. Okay, if our degree is higher in the numerator than the denominator, we have an improper fraction. When we have an improper fraction, is division possible? Yes. So to find our slant asymptote, we are going to perform long division, or synthetic division if it's possible, okay? And whatever the quotient is our slant asymptote. The nice thing, we don't have to worry about a remainder, okay? I don't care what the remainder is. There's probably going to be one, but we're only worried about the quotient part of it, okay? Okay. So if you have a slant asymptote, we're going to find it by performing division. Are you ready? We're all masters at division, right? Yes. Here's our example. Okay, notice how our numerator has a higher degree than our denominator. Since it is higher by 1, then we're going to have a slant asymptote. Okay? Now, I'm going to perform long division so that we remember how to do it. It's been a few days. I know you all are masters at synthetic division. Okay? We have a missing term, so we need to put a 0. Some of you forgot that yesterday, right? Okay, so let's remember how to do this division. X goes into x squared how many times? X. We take x times our divisor, and we have to do what with it? Subtract. What are we left with? Negative 2x plus 0. X times 1 is negative 2x. Negative 2. So we have negative 2x minus 2. I don't care what the remainder is. It doesn't matter. The remainder does not matter. All I care about is this right here. Okay? Our slant asymptote is at y equals x minus 2. We're going to get the equation of a line. Do not worry about the remainder. It does not matter. Don't find it. Okay? So our slant asymptote is at y equals x minus 2. Where is our vertical asymptote? Okay. Our vertical asymptote is at x equals negative 1. If you just write negative 1, you will not get credit for that answer. X equals negative 1. Okay. So, I'm going to graph my asymptotes. X equals negative 1. Do you know how to graph a line?
Yeah.
Yes. How do we graph this line? What do we plot first? The y-intercept. And then we have a slope of 1. If you need to use like an ID card or a ruler to help you get that line, that's fine. If you want to draw it and then erase so it's dotted, that is fine. Okay? So now we're still going to pick points, okay? Okay, since our vertical asymptote's at negative 1, let's pick 0 and 1. When we plug in 0, what do we get? Thank you. And when we plug in 1, what do we get? Okay, so let's talk about what would be happening, okay? Obviously, it just doesn't go straight from one point to the other, right? We're going to kind of dip in because we need to follow our asymptotes. Okay. On the left side of our asymptote, I would pick negative 2 and negative 3. What do we get when we plug in negative 2? We get 6. Positive 6? And we'll get negative 6.
Negative 2 squared is 4 minus negative 2 we get positive, so it's not 6.
And then negative 2 plus 1 will be negative in the bottom.
Oh.
So negative 6. What about negative 3? What do we get? Negative 6? Okay. That makes sense, right? So we're going to have that same thing happening. We're just going to follow our asymptotes. Okay? You do not have to tell me the range of 1 with a slant asymptote. One less thing to do. But what is the domain? What's the domain? Everything but the vertical asymptote. Okay? So, what is different this time compared to Algebra 2? Okay? One new thing, if we have factors that cancel, we get a hole. Make sure you graph that hole. Find where the coordinate of that hole is, because it needs to be excluded from your domain and your range. Okay? Second new thing, graph with slant asymptotes. How do you find the slant asymptote? You actually do the division of your polynomial. Okay? Here is your homework.
Wait, is Parallax with you or is tomorrow?
Tomorrow.
You're doing it.